Okay. Can you see my screen? Can someone confirm it, please? Okay. Thank you. Okay. So I think I had some questions on static timing analysis. Let's see whether you have understood clearly or not. Okay, there are two flip-flops here. For this guy, T setup time is 6 nanosecond. T hold time is 3 nanosecond. And T propagation delay is 10 nanosecond. Okay. And here T setup time is 7 nanosecond. T hold time is 4 nanosecond. T propagation delay is 11 nanosecond. Okay. And these are all the just a basic D flip flops. Okay. D1, Q1. This is D2, Q2. And these are connected by a clock. And it's the same clock. So what is the maximum clock frequency that you can apply? And they're connected like this. Okay. And this is some external input K. Hmm? And this is Q2. So setup time is given, hold time is given, propagation delay is also given. Okay. Anyone got the answer? So this is based on the previous discussion that we had. So if any of you were absent, I recommend you to watch that video, and it is always uploaded in the YouTube. Just watch it and then you can answer this, no problem. Okay, so what is the answer? Anybody got the answer? So sometimes, see, this is generally also written as clock to Q delay. Hmm? Okay, do one thing. You guys try to find the answer for this, and you mail me the answers or any questions that if you have. Oh, somebody did this. See, that's very simple. See, what is it we need to find out? We need to find the time period, right? So you apply the clock, how much time you should wait, right? So once you apply the clock, right, here, this is external input, okay? Think that we have some control over that. Now, the data that is going to come, right, once you apply the clock, then the new data will come here after 10 nanoseconds, right? Then for the data to be ready here at this point, you have to wait for 7 nanoseconds, right? That is a setup time, right? 7 nanoseconds. Are you getting it? That means for the data to be ready at this point D2, okay? So we just need to wait for this much time. Within that, you already have 11 nanoseconds here, so Q2 will be ready. That will be taken care. Anyways, this Q1 is already we talked about it, 10 nanoseconds. So this is the minimum time that you need to give for the clock. This is clock to Q minimum. If you want to wait for more time, that's fine. But you cannot wait. I mean, you cannot go below 17 nanoseconds. It should be above 17 nanoseconds. Anything is fine. Right? So obviously F clock is 1 over T clock. This is maximum means this is minimum. So this is 1 over 17 nanosecond because they are asking about frequency, right? So this is around 1 by 17. You calculate how much is this? 10 power 9, right? And then this is 1000 divided by 17 into 10 power 6 is mega, right? This is this many megahertz. See, for you to understand a clear concept, you just go back to the last week video and then understand what exactly is this. We discussed everything in detail. So, all right. And also we saw condition for checking hold time violation. And I just leave it to you whether the hold time violation exists here or not, right? So that's how it is. Very simple problems. These kind of problems may come in the gate. So, right. Now you solve this problem. Let's move on to the basics of sequential circuits. So this is a RS latch, and for the circuit shown in the figure, if S is 1, R is 1, then Q is what? Also, want to tell you that one note is there that we have discussed some of these problems in this phase 1. So you are always open to ask any questions from any problem. Okay, so I'll be showing some questions. If you have any thing to ask me, you can start doing that. You can ask me. You can just unmute yourself and ask. No problem. Okay, Anil, thank you. Hmm. Yo, answers for this question. Type it in your chat box. Which option? Okay, somebody said B. Mohan said A. Hema Prakash said B. Okay. Okay, I'll just give one more minute. Let me see. See, this is a two, I think 1 mark or 2 mark question actually. It's a gate question. Hmm. Any other answers? Mhm. Okay, let me pick up randomly option A. Okay, Rajat, what's your answer? Huh. You think A? Have you seen the question? Very good. Nice. I understood. Next. Mm, okay. Prerna Verma. Prerna, are you there? Okay. Bunty. Okay. So I'm revealing the right answer. Answer is C. See, if you take any digital circuit or any logic circuit, does the circuit show don't care? Does it display don't care? No, right? Either it will show a 0 or a 1 or 1010 kind of toggling kind of thing may take place in all those things, right? Correct? So before we enter into the answer, so these are like NAR based gate latch, right? NAR based latch, NAR gate based latch. So we know NAR gate, right? A, B, this is A plus B whole complement, right? If A is 0 or B, like let's say if A is 1, B is 0, or A is 0, B is 1, A and B both are 1, 1, the output is going to be 0. Means that if one of the input is 1, the output is going to be a 0, right? So since R equal to 1, this is going to be 0. S equal to 1, this is also going to be 0. That's the answer. Any questions? Anybody got confused with this? Please type in your chat box if you are confused. Okay. And then it's clear, right? So we'll move on. This one. What is race condition in NOR based SR latch? This arises when S equal to 1, R equal to 0. This arises when S is equal to 1, R equal to 1. And when we make S equal to 0, R equal to 0, then output become unpredictable. This arises when S equal to 1, R equal to 0, S equal to 0, R equal to 1, none of them. Option B. Okay. Okay. Option B is right answer. See, the answer is here actually. If you look at it, so when you make S equal to 1, I mean S equal to 1, R equal to 1, Q is 0, Q bar is 0. Then this is 0, right? This is coming as a feedback here. This is coming as a feedback here, and then it is 0, right? So what happens is still R equal to 1, S equal to 1 stable. 1 plus 0 whole complement is equal to 0, all right? So the 0 will be stable. Now what happens is here if you see when S equal to 1 and R when we make S equal to 0, R equal to 0, okay? Let's say you make this as 0 and 0. So according to NOR functionality, what should happen? Okay, these are all previous, right? So 0 plus 0 whole complement. Yes or no? Then 0 plus 0 whole complement. Okay, this is 0 plus 0 whole complement. That is also 0 plus 0 whole complement. Now you tell me which one will become 1? Whether Q becomes 1 or Q bar will become 1. Okay, that depends on which gate process faster, right? If N1 process faster, then Q will become 1. Otherwise, Q bar will become 1. If this process faster, then this one will be applied here. This one will come here. 0 plus 1 whole complement will be 0, right? If N1 is faster to N2. If N2 is faster to N1, then the entire equation will change. That means this latch is not working based on R and S, but this latch is working based on the internal details of the components that are used in the circuit.
which is not desirable at all. Okay, so the latch should work on the functionality of R and S. And you know that, over a period of time, components may degrade and they may behave differently at different times with respect to different temperatures and all those things. That means that you are certainly going into some kind of unpredictability because how the components degrade, we don't know. It's random in nature. Anything may happen. Okay. So that's the reason we cannot say exactly that N1, will always produce output as 1, or we cannot say that N2 will always produce output as 1. So it's uncertainty. So that is what is given here, right? Okay. What about this? So this is a basic JK flip-flop, and present state is Q, then the next state is dash. A simple question. So okay, Bunty has shared some questions. I think Bunty 44 question is similar to what we discussed. It's a repetition, so just consider doing that on your own. Mm. Question number 42 and all these things. Okay, answers. Option C, correct. Mohan is saying C. Anand Gaurav, where can we access questions? Okay, these are all the questions that I prepared uh, based on the kind of questions that were given in instrumentation and ECE and computer science from last 20 years. And then I just picked up some questions to get a flavor of what kind of miscellaneous. Miscellaneous means if you only know the basics, then you can answer that kind of questions. And I picked it up and then just kept it here. So, all right. So, see, for this question of questions, no, what is that they're saying? You don't know whether it is 0 or 1, right? Present state of the flip-flop is Q, right? Something. Then the next state is when the clock pulse is applied. Sorry for my handwriting. It's very bad, I know that. And we know that next state of a flip-flop, of a JK flip-flop is this, right? JQ bar plus K bar Q. And again, this entirely we have discussed in the phase 1. Okay, please watch those videos. Everything is there in my YouTube channel. Okay, you guys want my YouTube channel? link or something? Yeah, yeah, sure, sure, sure. I'll just share it. Okay, this one. So we had around 9 live sessions in the last phase where we have discussed extensively. This is only for problem solving or if you have any questions to solve that. So anyways, Bunty, you have shared some questions. Next week we'll discuss all those things, right? Uh, but anyways, even though they are simple, you can try attempting it, right? So j q bar plus k bar q. Now what is j here? J is connected to q. What is k here? K is connected to q bar, right? So j is connected to q, k is connected to q bar, right? Means q bar plus k is q bar, q bar, q. And so this is 0 anyways. Q bar complement complement. This is again q dot q is an q. So the answer is C. Good. Most of you are right. So no need to discuss much about that. Now you solve this problem. Initially, JK flip-flop is stored with 1. If the clock is applied, what is expected output at Q2? Okay, which option? A, B, C, D? Okay, option A. Okay, fine. A, B, something I saw. So, fine. See, this is what is the symbol of this guy? What does it represent? Negative, edge, triggering, right? That means that if the clock generates 1 to 0 transition, right, then the corresponding function will be performed, right? Now, just now we saw this, right? JK flip-flop, right? JQ bar plus K bar. If I take this for a JK flip-flop, right? T flip-flop is just a extension of a JK flip-flop, right? You have J, K, and of course some clock, Q complement, right? These two are connected to the same input, right? This is T. So you know that Qn is JQ bar plus K bar Q, where J equal to K equal to T. So your Qn is what? TQ bar plus T bar Q, right? What is this? T XOR of Q. If the clock is, if the clock enables the flip-flop, right? If the clock doesn't enable, then the same state will repeat, right? Now let's see. 1, 1 on JK flip-flop, that means that this is in toggling mode, right? Saying J equal to 1, K equal to 1 is also equivalent to saying T equal to 1 also, right? Right? I'm just talking about T flip-flop. Don't get confused here, right? 1, 1, and they're saying if the clock is applied, right? Let's say the clock is applied, that means that it is enabled. What is the initial value of the flip-flop? JK flip-flop is stored with 1, right? That means Q1 is 1. Now it's in toggling mode and you apply the clock, what will happen? This will become 0. So 1 to 0 is a negative edge, right? 1 to 0 is a negative edge. So this flip-flop will be definitely enabled. So accordingly, what will happen? Expected state or expected output Q2n is nothing but what? T XOR of Q2. So what is T here? T is Q2. Are you getting it? See, this T, Q2 is connected back to T, right? So Q2 XOR of Q2, that is 0. So the option A is right answer. Okay, let me see. Anybody has any questions on this? Many people say D, huh? Are you guys clear with this? Say yes or no through your chat box, please. This is a live session, right? You need to talk. Can we solve it without equation? Yes, of course, you can solve it. You have a this one, right? You have a truth table. You need to write the truth table, and it's a big drama, right? So this is straightforward and easy. All right. So let's move on to next question. Solve this. The state diagram is given. So X is don't care. Okay. Observe the state diagram of certain flip-flop. Q is present state. Qn is next state. So what is the relation between Qn, M, L, and Q? Read this. Do this properly. So which of the following is true? That's the question, kind of. Bunty, I think you haven't seen this question, right? In the last phase. Yeah, try this. Great. Okay, option B. See, sorry, option C. Okay, no issues. I'm not saying the right answer. Okay, I'm not saying the right answer. I'm just saying what the people said. Okay, right. So, see, for this to arrive at this, for this to get it right. So, if you remember the flow, right? First of all, you have something called characteristic, right? Table. Then from this, you have something called as truth table. Then you have something called as characteristic equation, right? Characteristic equation. Then you have state diagram. Then you have something called excitation table. Again, all these things in detail we have discussed, right? So please go back and then check it out. So you need to obtain this characteristic equation from this excitation table. That's very much easy actually. Do this, right? Mm. So if I write this, so let's go back to step by step. Mhm. So you have L, you have M, and you have Qn, right? I mean Q and Qn, right? This is Q, this is Qn, right? So first combination is this is 0 to 0. Initial state is 0. Next state is also 0. Further combination is what? 0. This is 0. This is right. Complement, right? Next. I mean, don't care. M should be don't care. Next. This is 0 to 1. Let's say 0 to 1. Okay, let me write this 0 to 1, 1 to 0, 1 to 1. Right? 0 to 0, 0 to 1, 1 to 0, 1, 1. Right? This is also nothing but excitation table. Right? Then to move from 0 to 1, what are the inputs you should apply? L equal to 1, M equal to 0. Then to move from 1 to 0, you need to apply 0, L equal to 0, M equal to 1. Then to move from 1 to 1, right? L is don't care, M equal to 0. Are you getting it? So now let's go to the truth table. L, M, Q, Qn. Okay, one straightforward we can do that, right? So these are the inputs, these are the outputs. Hey, don't get confused when I say inputs, how Q is an input and all those things, right? So for a sequential circuit, next state depends on the previous state, right? So this is the previous state Q. That's what I mean by when I say inputs, okay? So you have this combination 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, right? All the combinations are there. 6, 7, 8, right? Right? Now, what is this actually? What does this mean? If L is 0, M is don't care, that means that Q will be, right? What does it mean? If L is 0, M is don't care. Hello, can you hear me? Hello, hello, hello. Hello, hello. Oh, sorry, I am not able to hear you guys earlier. Okay, so just a minute. I just switched on to my Wi-Fi. I think it's transition from that. Okay, all right. Let me share the screen. Okay, now you see this here. Let me put it slideshow mode. Now, what does it mean? If you are at 0, if you apply L equal to 0, M equal to don't care means what is it they are saying? M can be 0 or M can be 1. Correct? If you are at 0, you apply L equal to 0, M equal to 0, or L equal to 0, M is equal to 1, then you will move to 0. That means if you say L, M, Q, let's say I will take this combination 0, 0, 0, then this is 0, 1, 0. Your next state is going to be 0, 0. Right? So here it is going to be 0, here it is going to be 0. Right? I'm just trying to decode this. That's all. Then the next condition. Let's see this. L equal to 1, M equal to 0. Then Q will move from, there is no other ambiguity here. Okay. 1, 0, then 0. I mean, output will move from, if you apply L equal to 1, M equal to 0. Where is L equal to 1, M equal to 0? Here. Right. When there is L equal to 1 and M equal to 0, then you will move from 0 to 1. L equal to 1, M equal to 0, then you will move from 0 to 1. If you have 0 as a present state. Next, L equal to 0, M is equal to 1, when Q equal to 1, 0, 1, 1, right? 0, 1, 1, you will move to, sorry, correct? Which one is this? 0, 1, 0, right? This one. Let me take another pen. Okay. So what about this 0, 1, 0? This we have already covered, right? 0, 0, 0, 0, 1, 0. Where is 0, 1, 0? We already covered this. Then 0, 1, 1, we have covered this. 1, 0, 0, we have covered. Right. Next, 0, 0, 1, 1, 0, 1. Your output will be 1, right? Where is 0, 0, 1? And 1, 0, 1. Okay. So what about other conditions? 1, 1, 0 and 1, 1, 1. What should we take? So guys, you're trying to understand, right, what I'm trying to say. Just I'm trying to simplify and decode it. Okay, what will happen to these conditions? L equal to 0, 0, 0, L, M, Q, 0, 0, 0, what will happen? 0, 0, 1, what will happen and all those things, right? So these conditions are not given. L equal to 1, M is equal to 1. Nowhere it is mentioned, right? So you can consider this as as somebody rightly said, you can consider this as don't care, right? Then you draw the Karnaug map, okay? So erase, simple Karnaug map, like I don't want to do it right now. Here, you can just, three variable Karnaug map. Try Karnaug map and then let me know what is the answer. So this is Qn, you have L, M, Q, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0, right? So Qn will become 1 when LMQ is 0, 0, 1, then 1, 0, 0, then 1, 0, 1. What about 1, 1, 0, 1, 1, 1 combination? Nothing is mentioned, so we can take it as don't care. 1, 1, 0 and 1, 1, 1. What is this? Is correct? Erase this. Oh shit, sorry. Where is 0, 0, 1? 0, 0, 1 is here. Then 1, 0, 0 is here. 1, 0, 1 is here. Sorry. I took a wrong step there. So you understood what the mistake I had done, right? 1, 1, 0 and 1, 1 were don't cares, right? 1, 1, 0, 1, 1, 1 are don't cares. Okay, guys, am I right? So you know the grouping, right? So you take a group of 8 ones, here not possible. Group of 4 ones, yes. If you treat don't cares as one, then we can combine these here, right? This is L. Then group of 2 ones is possible. This is M bar Q. So the answer is Qn is L plus M bar Q. See, since I'm explaining this, this will take some time. Otherwise, it doesn't take much time. Okay. So next, you solve this problem. Okay. Okay. We have two more problems. Let's solve it. Which of the following represents the state diagram of the circuit shown in the figure, where S naught, okay, S naught is a select line. This is 2 by 1 mux. See, for this simple way is you start with assumption of Q, right? So you assume Q equal to 0 or Q equal to 1 and start, right? So if you assume, let's say I'm at state 0, right? Very simple. You are at state 0. That means this is Q, right? You are representing Q. Q bar could be 1, right? Okay. So this input is 0, this input is 1. Now, if you choose S naught equal to 0, what will happen? Let's say, for example, S naught equal to 0, if you choose, this particular data will be passed, right? This 0 will be passed. If this 0 comes here, and assuming that clock is available that time, t is 0, we know that t equal to 0 means no toggling, right? No toggling, right? T equal to 1 means toggling. That's how the name came, right? Toggle flip-flop, right? So t equal to 0 means no toggling, means the output will remain the same. You understood? Now, suppose you are at 0. Let's say you have chosen s not equal to 1. What would have happened? Instead of this data would have come here, right? This one would have come here. This one would have come here. Now, this is a toggling condition, right? So, your q is 0, right? So, the toggling will take place when s not equal to 1. So, your output will move from 0 to 1. So, can you solve it and tell me what is the right answer for this? I just gave you an idea. I gave 50% of the answer, by the way. So, state diagram of the circuit means they are referring to Q. Okay. Okay. What's the answer? Option C. Okay. Somebody asked. Oh, Anand, is it necessary to take Q as LSB? No, you can see, you can take that as MSB also. You look at this. If you take this, okay, let's go back to this question. I am here, I am considering Q as, let's say, you can take in whatever way you want. Accordingly, your Karnaug map also going to change. You understood, Anand? There is no requirement that Q only has to be LSB or Q should be MSB or something. You can take in whatever the way you want. You can put the Q in the middle also, right? But accordingly, Karnaug map will change. Finally, eventually, you're going to get the same Karnaug map. That's what I'm saying. Eventually, the final answer is going to be the same. Okay, so let me solve this. Now, okay, now anyways, there is no ambiguity, right? In this, now what are we doing? We are assuming I already done for the first part, right? So let's assume Q is 1. Obviously, Q bar is 0. Now we are at here, Q equal to 1. Now you apply S not equal to 0. What will happen? This one will be passed here. This one will come back here. The clock is available. Then there is a toggling. So S not equal to 0. Right? Obviously, the other one is S not equal to 1. Correct? So which option is this? Option C. Perfect. Option C is the right answer. Okay, solve this problem. Very, very simple problem. Okay. It's a combination of mux and flip-flops. I think it's a very simple problem. I think I'll close the session now at 1. If anybody has any questions to ask me, please mail it to my mail ID. I'm just going to share it. Any specific questions that you want me to discuss, I will discuss. Anyways, Bunty has shared. I am going to discuss some of the questions. You mail me those questions, then we can discuss next week. Otherwise, according to the theme, I think next week is going to be combinational circuits, right? We'll discuss miscellaneous problems and combinational circuits and other things. Okay, guys, I just wait for 2 minutes for taking up any questions. Otherwise, you can leave. We're good to go. From where we get these questions? Okay, sis, as I told earlier, I have taken these questions from last 20 years of papers from EC, instrumentation, and other things. I just picked up few questions and then you want to access these questions? That's what your question is? Okay. Just mail me. I'll just share those questions. Okay. I have a document. Or is it possible to share the document here? I don't think so. Is there a way to share the document in the chat, Sneha? Do you know? I'm I'm pretty new to this actually.